while the intelligence squared debaters avoid that type of fallacy, you'll notice there's a particular style of debate that kind of happens throughout them, and we'll be listening to a few of them at a time. But one of the things that they'll always go to, I want you to listen for it, is the appeal to emotion, that pathos fallacy. You'll always hear them, and they'll also do the fallacy that results from taking a single example and making it the sort of the norm for everyone. Like you talk about, you actually heard it during the gun debate, where it was like, if just one person were saved by the banning of this weapon, then it's worth it. And so the question is, well, does it actually do what you're saying it does, and all that kind of stuff. But you'll hear that in the intelligence squared debate. It's just, you'll hear that like, I know this person, they do this, therefore carry the motion. And the motion is much more broad than their initial example. So make sure you have your notes out, your iPad out. We're going to be continuing week 11, natural science. Again, your argue it out was evolution, your philosopher portrait. Either learn a little bit about Charles Darwin, a little bit about Copernicus, depending on if your teams 1 through 3 or 4 through 6. I wanted you to also look at, it's about 10 minutes, and then this one's about, the intelligence squared debate's about an hour, and the Ben Goldacre is about 10 minutes. So give yourself time. You can listen to the Intelligence Squared as an NPR like podcast, so it gives you highlights, and it's also a little bit, it's just in the background or whatever, you can listen before. But I want you to take some notes on it, maybe 3 points on it. So if you even can't, if you're really strapped for time or whatever, just listen to at least one of the motions or one of the rounds of the debate, and listen to what they said, or maybe just the conclusion of the debate, and you'll find some interesting interactions to discuss, because I do want to have some content for you to discuss next week. And the Ben Goldacre is just fun. He's a funny guy. I said that he was a journalist, but he was more than that. I actually found out, because I re-listened to it, that he's a doctor and a researcher, and he's now what he calls an epidemiologist. And it's a field of science that discusses all the problems that happen with the thinking of science in popular culture. So it's like a pop culture study. So I think that's pretty interesting. We're going to kind of talk about that a little bit today. I want to review I have 3 ideas that I mentioned on Monday regarding our discussions this week. We've been talking about really what amounts to just this first central idea, which is scientific notion seems to be this kind of changing system, but there's definitions involved in which, for whatever it is, and I asked you guys to look at it, to create a definition based upon some of those quotes. Some of them were more creative quotes and sort of this use of language to describe scientific knowing. Others were a little bit more experimental or applied. But what we do know is these kind of things about observation, that scientific method that seems to have been developed during the 18th century. Observation, experimentation, and some type of combination of inductive and deductive reasoning. Remember, inductive is to go from the big to the tiny. Deductive is from the tiny to the big. And so theory versus the application or experiment, or is it experiment to create our new big idea or theory or paradigm? So this is somehow involved with our central idea. We're not done yet, because we still got to talk a little bit about observation. We're going to do a cool activity today to show some interesting uncertainty involved with observation. Yes?
Deductive reasoning is the one that Sherlock Holmes uses?
Exactly. So deductive reasoning is what often people think he's using, and it makes a lot of sense, because you think he's going from the small thing to the big thing. But a lot of the time he's actually utilizing inductive reasoning, in that he's actually going to construct a big theory and piece it all together using the smaller parts. Yeah, so that was actually something in the Plato and the Platypus. They actually mention often people think of it as deductive, but it was actually inductive. It's sometimes counterintuitive, because everyone talks about it as being powers of deductive logic, including the author himself talking about Sherlock Holmes, that he's using deductive reasoning. Deductive means you have no theory, but Sherlock Holmes always has some sort of theory in mind that he's going towards.
Yeah.
That he's moving towards, that there's a person involved. He already knows the theory, now he's got to corroborate the evidence based on it from what he sees. And then he'll change course as he needs to, as the evidence proves or disproves. So that's an interesting tension in science in general. Do we only go where the quote-unquote evidence leads us, or do we have something in mind, like a hypothesis in mind about what it's going to do? one of the things that we're going to talk about today, not to get too ahead, is the use of science as accident. Things that kind of, but then you find something, and literally it changes everything. And is that science or not? If it comes out of bad science or discoveries not previously intended. Second idea here, so these are just simple. This is definition, just in one word, definition. Number two, this is it as a language or some other type of human thing. It's a human identity or processing. It kind of reveals something about we as humans. Why is it that we seek out science? There was a Dexter's Laboratory episode. Do you remember this one? It was like a mini movie or something on Cartoon Network where it was imagining a world without science. It was actually someone who was so smart. It was that other guy. Who's that other guy that... You guys ever watched that show?
Yeah.
That's kind of
the tall one.
The tall one. There was like a tall one. Ha!
He was like red.
Yeah, and he took all the science away from everybody and like was hoarding it for himself. And Dexter had to go and rise up this new scientific revolution. It was a future episode, but everyone else was living without science. They're rolling around in the mud. Sort of that Monty Python kind of look. A witch, that kind of thing. So, what is it about humans that we necessitate science all the way back to the beginning of man? So this is kind of this is a broad anthropological look at science. And this third one then is about whether or not this science then has an interaction with community. That we are not just individuals, but we also interact with you and I together, learning from you, you learn from me. We share data and also critique one another. So is there an apparatus involved with science? We talk about science as like a quote-unquote the scientific community. So there's a group of people that share some sort of creed, and that creed is not necessarily a religious one. It is, however, something that guides the process. And that idea of creed then is important because so often communities clash, and different ideas and paradigms even today clash with regarding scientific knowing and what would be considered authoritative knowing, or maybe religious knowing as a different thing. So there's interesting debates on both sides. This third one's going to dominate next week. So when we talk about science and religion, we're going to be doing that. So we're going to be gearing up towards this idea. We'll give you some thoughts to think about for next week, and then you'll have a Socratic seminar in which we have a discussion on it. And you model that language for us. All right. The bedrock of science. This is a new slide for you. And as I discuss these topics, remember, this particular lecture has a lot of like little activities brought into it. So a little fill in the blanks and that sort of thing, ordering of stuff just to keep us a bit focused in our notes on processing the information. Observation, to observe the world. You can't do science unless you're thinking about it and seeing what you're doing. So how might this interact with these other ways of knowing? Did I show this slide already? I don't remember if I did. I think I might have already slide because I already asked you to kind of put these in most important regarding observation. I gave you the 4 ways of knowing here. Intuition can be considered part of emotion, so technically there's only 4, but I 1, 2, 3, no, I have 4 there. So then I have reason, emotion, sense, perception, and can't remember that. Let's just use intuition as a placeholder. Observation. How might, from these ones we mentioned, perhaps that sense perception seems to be the highest. We had a kind of consensus on Monday of that. And what might be the lowest one, you think? Maybe emotion. How might, if we were to compete, what might be the 2 that compete together for the lowest one? Yeah, we seem to think that emotion and intuition seem to be on the low spectrum of what we would call observation, or observing the world. That when we observe things, we aren't doing it from an intuitive stance, rightly. We're doing it from a reasoned stance. But is this actually true? So that might be something we'd want to experiment or test. Do you, as a human being, spend majority of your time reasoning through the observations you make about the world, or are you intuiting them, meaning you assume certain presuppositions that you're not actually reasoning out in some sort of logical format in order to produce a result? So this is something to consider when we relegate intuition to a low level. Scientists might actually defend the fact that intuition helps them. They seem to know things based on routines and other things, even though they can't describe what they're doing, to kind of make conjectures, and then perform experiments that lead to discoveries. Yes?
I was just gonna say, I feel like in Sherlock Holmes remember when we were talking about how Sherlock Holmes was counting the stairs,
Yes.
and forgot the doctor's name?
Dr. Watson.
Watson, yeah. He represents maybe more the common man that just uses intuition. He goes about their day-to-day life without really thinking about anything.
Yeah, Watson's a great foil for Sherlock because Watson, even though he's a very smart man, he's a doctor actually. He was an army veteran and that sort of thing. Lots of wars that he was a part of. Is someone who kind of goes about his daily life using basic intuition. Has learned a lot from Sherlock Holmes over the years, but Sherlock has that constant, what seems to be a constant induction of the world based upon observations of the world, focusing very strongly on those minute details, memorizing them. But when he'll actually make statements, I wish I had the quote. I actually have the quote. Let me just go back to this. I actually put in this quote, it's funny that you brought that up, back to that original quote of how many steps are there in coming up to the coming up to our apartment? Well, 17. It's because you've seen but you haven't observed. So I've said that before. But there's other quotes with Sherlock who talk about, I maybe am not able to describe my process. When I go into a room, I just sort of see it. And then the new movies with, what's his name in it? His name is Sherlock. Robert Downey Jr. does a great job of kind of that like sort of Sherlock time or whatever that he creates, where he sees everything at once.
Oh.
And you can't he probably can't explain to you what that feels like, although the cinematography gives you an awesome sense of that. When he's like analyzing,
it's like one.
Yeah, one. It's hit in the carotid artery.
Yeah.
Knock him out or whatever. It's like paralyzed. Yeah, and then it's not for Pac-Man. Yeah. So all these, that Sherlock time is very interesting because he talks about it as intuition. That intuition, he places his intuition much higher because after a course of routines, years and years of researching and practice, you kind of just get good at something and you know how to do it implicitly. It's like really good football players or in sports, you kind of get used to it and it's that theory of, what was that, truth, there's like different types of knowing. There's that knowledge of, there's two different types of knowledge. The description knowledge and then the acquaintance knowledge. I always think of acquaintance like knowing how to hit a baseball. You can tell, you can talk about it or you can do it. And there's something, so intuition is about doing science as opposed to describing science. I'm a knowledge by description guy with science. I don't do a lot of scientific experiments. I think that scientists might have a higher or different view of it. So just to think about that, because we do have a different, we have a set that we think about, but it might be a little bit more broad than we consider it to be. Observation then, to have observations are so important. Haley, can you turn off the lights real quick? I want to describe to you a really cool experiment that I learned about my college year. I actually took a class called Science and Theology, and it was in a symposium course talking about the very things that we're going to talk about next week. But one of the cool little experiments that our quantum physicist that was co-teaching the course with a philosophy teacher described this double slit. You guys ever heard of the double slit experiment? Oh, perfect. I want to start with the what's an element that is required for observation? I'm thinking as a scientist right now. Huh?
Carbon.
Carbon. Okay, why do you need carbon? Okay, so that's a good one. If there's no building blocks of life, there will be nobody to observe. Perfect. What else? Let's say that we have life forms. Let's just get right to that. You have life forms. What do you need to observe? You need like other things. Let's assume that's there too. You have life. You have eyes, so you're good. But what about the fire specifically? The heat?
Yeah.
Maybe.
Yeah.
But what more specifically than that? I just turned off the light. Observations often require light, right? You need to be able to see usually what you're doing. Usually, I mean, you can observe things with other senses, but this is where I was going to say. You guys were all having right answers, just not the right answer. For what I was thinking.
Which element, we went straight to the periodic table.
So I was thinking of I'm thinking of the insane clown posse kind, like fire, water, earth, dirt, effing magnets. How did they work? Right? That's where I was going. Like just light. Isn't light like an element or something? Isn't that on the periodic table? Light, Earth. It's like the Captain Planet, you know. Heart. It's Do you guys ever see the Funny or Die of Captain Planet, where he just like starts killing everybody, like turning everybody into trees? And it's Don Cheadle. It's really funny. Like
I really want to see
in Napoleon Dynamite, the Pedro is in it as like the South American heart. You know, he does that kind of thing, and they all come together, and Don Cheadle becomes Captain Planet. You guys know who Captain Planet is? No? God, you don't even know who that is? Oh my god. That's like 90s cartoon. Okay, never mind.
By the way, really quick, Mandark, that was his name.
Mandark?
The Dexter's Laboratory.
Oh, thank you. Yes, yeah. Haha! You guys, yeah. God, this is like a 90s cartoon day all of a sudden. Didn't realize it. Yeah, anyways. Learn who Captain Planet is.
Light.
And then you'll be funny with it. Light! Okay. What is light?
Energy.
It's some sort of energy, yeah.
Archetypal.
That emits something that we can see in a visual spectrum. What is light?
Photons.
We call light as we have like this spectrum of stuff. It's like photon. We use this word, this language to describe what it is. Use the word quantum. There's something quantum-y about it. Quantums. Okay. How do we tell different types of lights? What is it about the science of it? Okay, so wavelength. So there is this experiment. In fact, this idea of wavelength of light with light waves, we take for granted. But there was in the 17th century, 17th and 18th century, a constant sort of discussion, debate about whether light is a particle or light is a wave. And so, yeah, you're getting ahead now, but thank you, Mr. Side. No, I'm just kidding. But there was a guy named Thomas Young who experimented with this and was able to put to rest indefinitely, so permanently at the time, not anymore, but that his debate between himself and another guy, Sir Isaac Newton, so kind of a hard guy to fight with. Newton had, amongst other things, done some cool work, but he had talked very dogmatically about the idea of light being a particle, that it was clearly a corporal thing, like it's a packet of something. So I want you to think of these in two terms. I want you to either think of it like water, so like waves, or I want you to think of it like beads, like a BB gun, like a gun that shoots. So those are the two things that we're thinking about, a particle or a wave. Now, Thomas Young's experiment does what you would think you would do with a particle or wave. You know the double slit now? Okay, so if I were to take a light source, let's say it's just a candle that I kind of lit up like he's in, because it doesn't have flashlights or LEDs or lasers or anything cool like that. He actually did a simple experiment where you take the thing, the light that comes out of here, and it goes through a little hole, a slit. Now that slit can kind of be one slit, so if it's just a single slit, you'll actually see a pattern that goes it's just a little bit wider, so there's like a wider thing. As the particles, the assumption is that the particles in the single slit will kind of bounce off each other and kind of flay out a little bit. So that's the idea, is that they're bouncing around. Now, but the experiment then is if you take two slits and you put it on there with the same candle. Okay, that was a terrible candle, sorry. Lobby candle, there we go. Let's try it again. There we go. You can actually see, instead of a single refraction, you can actually see what is called an interference pattern along it. What is an interference pattern? What do you think interference means? I'm going to show you it right now. You can do this at home, a little do-it-yourself experiment. You can buy like a $10 diffraction like screen, or you can just use a CD. And this is kind of cool because not only, CDs are actually read by what? A laser. You can actually read it by using a laser. Instead of reading it like a computer would, we'd read it like a math would, whereas we'd figure out how much data is actually on a CD by its refraction patterns. This is an interesting thing. We're not going to do it because I don't know how to do that. I'm not that smart. But what we can see is that as a result, I'm just going to show each person this as I go. I got to find the refraction. Do you see? Eric, do you see those extra little dots with it that are right next to it? That's what you're looking for with that. So I'm going to show you. All right, see if I can see those. Yeah. Okay, so the single dot. I'm just to tell you the laser is a single point of light, but when you do the, I don't know if it'll work on the couch or not. I know there's several different reflections, but that's not what I'm looking for. I'm looking for the refraction or the interference pattern. There it is. You see the interference pattern? you could actually measure those to tell how much data is on the CD. Because they're little, they act as slits, just like you would in a piece of paper or glass, just literally slits inside something. And the light goes through both of them. As a result, you see the refraction pattern there, you go right there, see it? So this interference that Thomas Young finds is actually what happens instead of BBs going through the slits. What goes through the slits? Waves. So when waves go through a slit, two slits I should say, they become two different wave patterns that then have corresponding pitches, like ups and downs. I'm not even sure whether they're sine waves or whatever they're called. The length of the wave, right, is that way? Versus the amplitude or something, right? Is it either one? Okay, so what they find is just like with two waves of oceans coming together, sometimes the waves will build each other up into a bigger wave, and sometimes they'll do what? If there's two of the exact same wave going in opposite directions, they cancel each other out. So there's brighter waves and then dark areas. Brighter waves, dark areas. And this is what's called the interference pattern. Now, so far so good. So we think for, a couple hundred years, everything's good. We know that light is a wave, right? Except when you start considering quantum mechanics. You get things really, really small. And after Newton comes on the scene, we start seeing something happen with really small light particles. And you use electrons, like the electron light sources. And so this is the example of that diffraction, that interference pattern that I talked about. If it's in fact a wave, this is how it will create lights and darks along the edge there. And I'm going to show you real quick more to the point of wave-particle duality. So this is the thing, it's kind of crazy, but consider what happens when you just use an electron. Electron we know is what? Is it a particle or a wave? It's a particle. It's like a thing, right? And so you think it would be like a BB that would shoot. And if it's a BB that shoots, then you would think it would create just, two different places and not an interference pattern. So they shoot these electrons, and what they end up seeing when they observe it on the back wall, just like I was doing it on the desks, is that the electron creates an interference pattern. It's like, well, wait a second. If we're observing this particle before it comes out of the electron gun, let's say it's an electron gun, shoots it, just like a BB, the assumption is, based on our inductive reasoning, that it should create, just like what all other particles do, which is a single pattern of going through the slits. Instead, they find interference. So then they say, well, maybe that's because they start deducing now that it's because they're bouncing off each other and then kind of creating this diffraction pattern that's not really interference, it's just them going all over the place. And so they're actually able to, and Einstein got a Nobel Prize for this, figuring out how to release electrons and create electronic light in that regard, to shoot an electron out of the gun one at a time. So at that point, they have nothing to bounce off of to mess each other up. What do you think they find? Same thing. They're going through and they're having an interference pattern. So I'm like, okay, well, what's happening? How is it that they're doing that? So this is what particle duality is all about when I say that word there. It's probably something to write down about observation. Because this is about breaking down our ideas of observation, is what I'm trying to get at. I know it's been a lot kind of dense for a little bit. What they had to describe with this is that the particle would actually interfere with itself. And it would basically go through both. The particle would actually go through both of the slits at the same time and then come back on together at some point, this duality, back onto the screen as a single electron, because they can actually see each electron going and coming. Now the one thing that wasn't observed, they could see the electron before it was shot out, and they can see the electron's pattern behind it. What's missing out of that observation? What's happening during it? So they assume that it's like doing this particle duality, where it just kind of literally splits apart, comes back together, and interferes with itself, so that it creates this interference pattern like a wave. So then what would you do in order to reduce that level of the lack of observation? You'd have to observe the place in which it's going through the slits, right? You think that they would have already done that, but they didn't, because they are only looking at the diffraction, their interference pattern. What happens though when you observe it?
It goes far.
It turns into a freaking particle. It doesn't do anything, and all of a sudden it changes, and it becomes like, it just acts like a normal particle. So no, it doesn't say that. I can't say that. I'll tell you why in a minute. When you observe it, it changes the experiment. Let that sink in for a second. Write that down. Sometimes when you observe something, you are changing the experiment. You are changing the experiment. How are you able to know anything about the world if you assume that you are changing the experiment just by looking at it? Right? There is this analogy that is as a philosopher's sort of paradox about, it's called Schrodinger's cat. Basically, if you're trying to figure out whether the cat's alive or not by peeking into the box, if the box is rigged so that it kills the cat before you can look at it, can you ever know if the cat's alive or not? It seems to be that the cat is or is not alive depending on whether or not you will or will not open it and look at it. And this is a little bit of a paradox. The same thing, and it makes for a good horror film, I'm sure. If you, instead of doing a cat, you say Schrodinger's human. Ooh, that'd be like a jigsaw, like would you like to play a game or whatever. Right? At the micro level, at the quantum level, this is sort of thing happens all the time where we're not sure how particles actually operate. Are they waves or are they particles? Now in 2012, this answer, we had like a little bit more answers. We're able to figure out an experiment where we can observe it and not quite mess it up. We seem to have the same kind of thing. So we're seeing it in this way. And so I want you to look at this. This is a very interesting video. It's just a quick little demonstration of what happens with each one of these examples. So go ahead and look at this real quick here. It's called wave and particle duality. They're going to start with our double slit, so you're just going to see what I just described. Here's our gun that shoots all of our particles. And this is our regular interference pattern where they're all interfering with each other or hitting off or bouncing. And there's no clear interference, meaning there's no wave. Now when we shoot out waves, if we have that amplitudinal distance, they go through there just like water would, and we'll hit each other in light and dark corresponding lines. So there's our interference pattern, just like you observed with the CD. Here's what happens at the quantum level. They're wave particles, or some type of thing that acts as both. And it ends up as an electron. It has a wave element, and then so that it interferes with itself, and then comes back as an electron when you observe it on the other side. You see that? Why does it do that? Because quantum mechanics is weird. I don't know. It's magic. So that's how it creates an interference pattern, because it's interfering with itself. It doesn't have the same type of time locality thing that we think of with normal objects.
So the observer will absorb the light.
So this is what will happen. Now we're going to stick our eye there. Uh-oh, and why did it stop? It's like showing you, ooh, look what's going to happen. Did it say that early? Oh my god. I did that last time and then it played just fine. Give me a second, let me just go back to it. Let's go back to our playback area here. We already saw that part, right? You ready to see that part?
Yeah, we're good.
Yeah, okay. We saw the interference pattern. Now, okay, so they're going to show you with the observer, when you go there, it turns into a particle, right, when you're supposed to see it. Yeah, stupid.
So the first one is how we think it reacts, it is, or
So it says no interference can occur when you are modifying the experiment with an observation of it. So how do you do science with a motivation? Now, if you're interested in figuring out the solution to this more than what they're showing here, I suggest going to look up there's two things that I want you to write down, just in case you're interested. You don't have to, but it's something that if this is fascinating to you, go look up more. First one is the delayed choice theory. And this is kind of like Schrodinger's cat, where they theorize that the particle waves are actually choosing based upon how you collect the data. Depending on if you collect it as one thing versus another, it seems to retroactively change the experiment, double choice. And we'll talk about why that's a fallacy. You see that in textbooks in a moment, so I don't want to give that away. But it's like it's alive, like, yeah, it knows. Sometimes we use this type of fallacy to describe the world as it knows that we're looking at it. Yeah?
Is it only like a person, or is the same thing happen if you put a camera?
It's not a person, so that eye is really kind of deceiving. It's more of a spectrometer or some other type of instrument to whatever it is to observe. It's our observation of whether it goes through one or the other slit, or both, or it does something different. But it seems like whenever we observe it, it doesn't do what we are seeing it doing on the other side.
How do we know if it's only when we observe it?
Well, it's when we don't observe that what happens in the slits
yeah.
that we find the interference pattern in the back. So we have to assume that it is a wave, because that's how waves operate. It's an interference pattern.
Why can't it be both at the same time?
Why can't it be both at the same time? That's a great question. Does science have some sort of predetermined creed that says, one object cannot be, in this place and this place at the same time? Well, we have sort of Newton's laws of physics. We have that kind of those things, but those things tend to not operate in a quantum world. So this is where Einstein changes the Newtonian paradigm. Can things be in two different places at the same time? And we know there's all sorts of reasons why that could potentially be true. Think of wormholes in time. I mean, there's a lot of outskirts to our understanding of stuff. The other thing, that was the first thing, the delayed choice theory. The second thing is the 2012 study of this. So look at 2012 double slit experiments. See if you can figure out how they actually are resolving this issue currently. And they're still continuing in the idea. So you saw the interference pattern, that's a little activity, and you understand this thing. So this is, again, touching on what it means to observe the world. Oh, another way that kind of continues with that idea of observation is whether or not we are getting the correct story before we begin the experiment. Can we predict or have some type of hypothesis? This is where inductive reasoning goes about. I'm going to go fast with this because I want you to, well, I'll give you guys like 3 minutes or so. You're going to read each of the sentences. I want you to try and put it in order based upon what the process of thinking should be. Okay, so you're just thinking about which one would come first, second, third. This is Stephen Hawking's book on time and space. So he actually has this really interesting chapter where he kind of walks through, just in general conversation, I want you to put it in a logical flow. Number one, these are all statements he makes in a single paragraph. I had made a mistake. Number two, it seems to me much better if you admit in print that you were wrong. Number three, the universe could have started out in a smooth and ordered or lumpy and disordered state. Number four, neither of these possibilities agrees with what we observe. Number five, the universe would become lumpy and disordered as time went on. Number six, one has to use a quantum theory of gravity. Number seven, some people never admit they are wrong. Give it 2 minutes. Can you reorder those so that they seem to make some sort of logical sense? Where would you start? Where would you end with this paragraph? You should just kind of write them down maybe in the order that you think they would be in. See if I have anything else. No. Yeah. Sorry. I'll go in right here. And I'll drink some coffee. This was a bigger class. We have a little bit more chatter, but that's okay.
Are we supposed to?
No, you don't have to chatter. Just look at it. Do we have something down, kind of? Just to make the statement concise. It doesn't change any of the information. It's that I'm trying to get. I hate silence. Thank you. Haley, what do you think might be a good starting sentence for us to think about?
I think
Number 3. Why number 3?
I like.
What kind of statement is that? Describe the nature of this language here. We're trying to understand what a hypothesis is. We're just doing it a roundabout way. We're not doing it definitionally.
And I just feel like that would be the one to like start off all of those, like start off the conversation with like that topic, I guess.
I think you guys agree, disagree?
I agree with
Number 3?
So it's like a
It's just like a
Yeah.
statement, like, and then you're gonna like elaborate on what you
Yeah. What kind of statement is it? It could either happen like this or like this. It's like an either-or type statement, or it's some type of research problem, perhaps. Hey, the universe could do this or it could do this. Is that a hypothesis? No. That's just telling us like what our initial issue is. Perfect, Haley. Thank you. Don't second guess yourself. You know what you're doing. What might be another question? So the universe could have started out in smooth and ordered, or lumpy and disordered. This could be our first sort of sentence here. What might be a second sentence? And there's maybe no right or wrong answer to this, so just kind of shout it out. What do you think? Number 6. So maybe we're starting to think, okay, inductively we know we have to use some type of quantum theory of gravity in order to determine what? My hypothesis, perhaps, or my experiment, depending on how I order this. So good, number 6 would be a great one. What might be the next one?
5.
The universe would become lumpy and distorted as time went on. What is the statement? What is that? There is your hypothesis. Do you see how the hypothesis is different than our last 2 statements? It's some sort of prediction of how things are going to be depending on your experience. And so Hawking here is explaining his ideas behind his hypothesis. It seems it would do one or the other. I've got to use quantum, and my hypothesis is that it's going to go into a less ordered state. So he had this whole view that the whole universe goes into less and less order as time goes on, and that everything would sort of, as time gets farther, as space goes farther apart, and the continuing effects of the Big Bang, we also have some other type of disorder and lumpiness. He calls it lumpiness. So there's all these funny language terms scientists use to describe these very weird phenomena. But the universe is going to get more and more disordered. What might be the next statement? Neither of these possibilities agrees with what we observe. Is there any observations first before, or no? Seems too much better if you meant the universe could. No, the universe would become lumpy and disordered. So so that's right. So number 4 is neither of these possibilities agrees with what we observe. So when we observe the world, he's finding that there aren't necessarily, we could actually be in a state of, we could actually be in a contracting state and still look like we're getting disordered. There's a lot of math involved with that, et cetera, et cetera. So here we've done the experiment, and he's determined that he's wrong. He's admitting it. He's not saying that he's this, it's not a dogmatic theory. It's saying, hey, I'm wrong. Now, what is it now as he's describing the end part of his hypothesis? What are the next statement, you think? 1, I had made a mistake. This is what you do with hypotheses. They're not things that you need to feel bad about making a mistake on. It's part of science. Science! And its way of doing things. But apparently it gets the insane clown posse really pissed when, because they're trying to explain things and they get stuff wrong. It's a miracle, don't you know? What's the next statement?
2.
So either 2 or 7. We got a little bit of conflict here. Why could it be 2 or 7? What is the difference?
I think it flows better. Some people never admit they're wrong, but to me it seems like it just flows.
Yeah. Maybe it could be either or. I think there's no thing there, but he's suggesting 2 things. What's this? Let's say it's 7 and then 2. What's the first thing that he is saying about this idea of being wrong in a hypothesis? It's okay to, and not everyone does it. What does it mean to admit something like you're wrong? You're owning up to it for yourself. So admitting that you're wrong is important, and telling other people. How is that different than this number 2 statement? Why might that be different?
Because in number 2 you have proof of your wrong instead of just like statement.
Yeah, so think about how, you might run into teachers. Not bagging on any teachers, because I'm a teacher. So. And I do this sometimes where I'll make something up accidentally just to kind of continue on. And it's not good that I do that, but I have to admit I really try hard not to, but sometimes I do. I'm like, bah, and I just throw out a word that just comes to my brain, and no one challenges it. Great, move on. That one hurt me. It happens. It happens. I had a history teacher that did that in class once, and he finally got called out because someone had asked a simple question. What was that date again? He's like, I don't know, I just made it up. Oh, that was terrible. He felt bad. No, he didn't. So, and it happens every now and then. It's different to admit it to yourself or in general, informally. It's another thing to admit it in publication. And this is where Stephen Hawking was really important on this number 2. It's much better if you print that you were wrong, meaning you clearly show and demonstrate. This goes towards the hypothesis as not just a single scientist in himself, but also a scientist in a community. And it's hard to do that because there's egos, there's funding, there's money, like not just funding, but like profit involved with the things that you do as a scientist. And to admit you're wrong is a hard thing. And some scientists do it, sometimes scientists don't. So this is where we get to what science is as a community. So we're getting close to that idea, question number 2. And the question that I have at the bottom here that I want you to consider is, how is hypothesizing different than the words prediction or other types of things like guessing? We can almost put that on a spectrum of language, couldn't we? Guessing, prediction, hypothesizing. What makes hypothesizing unique as a scientific definition over and above these other usages that are similar to that idea of future knowing? You maybe give reasons, you actually go through a process, not just a single thing.
Use theory.
Use theory, so there's inductive reasoning there. Haley, can you turn on the lights real quick, just so that the video...
Prediction, you're trying to figure out, like you're trying to actually guess the outcome, like get the outcome of this one. It's testing.
Oh, I see how you're saying. Guessing might be you're trying to, that is in fact what it's going to be because I'm guessing it. So it's like our Monty Hall problem that we described with the 3 cups. I'm guessing at one of them because I have no methodology, although we found that there's at least one methodology to increase your chances. But initially you have nothing but your guess. Prediction, sometimes we hear the word prediction like political analysis or like a fortune teller. They're going to predict the future, something along those lines. You don't hear of a fortune teller hypothesizing the future, right? I hypothesize, because what would that entail? What would that do to their profession? To hypothesize it. That actually has truth base, that it actually is contingent on whether or not it actually occurs, and at that point you say, I was wrong. Do fortune tellers ever admit they're wrong? They get around it all sorts of fun ways, which you can explore if you want. By the end of next week, I'll have you do an activity in your notes for us. Experiment. Do you guys like Back to the Future? Love Back to the Future. For all sorts of fun, bad science reasons, but also part of it because, I don't know, Doc Brown's just a cool character. He seems to be a failed inventor who, in a moment of serendipity, which is a word that we're going to use in a moment, discovers time travel just by falling and hitting his head. But is that how experiments normally work? Through serendipity. There's 2 different ways in which experiments yield results. How did we get the light bulb? Do you guys know this process? Edison, right? What did he have to do in order to get the light bulb?
Oh, you're talking about the kite thing?
Not the kite thing. That's Franklin, right?
No.
Or did Edison do that too?
No, that was, wait.
Yeah, I think you're getting electricity mixed up with the light bulb. The light bulb, if you've ever read the story of Edison, it's very interesting. He actually had filaments that he'd have to test, different types of conductors that would light up really bright. It's what all, not these, because these are gas. These are like cathode-type fluorescent lights. They're sealed. Anyways, the normal light bulb is the one that cost a lot of, or that waste a lot of energy nowadays, because they have the energy-saving ones. They had a little filament that lights up really bright when you put heated electricity through. And he had to find one that would do that, would light up and not burn out. And so he had to do these tons of materials over and over again. So his experiments was about trial and error, not millions, that'd be long, hundreds and thousands of times, right? So something like that. There's actually the story about it like piling up, these filaments piling up by the side of his room, just kind of because he had so many of them he was going through before he found one that worked. That's a type of experiment. There's other types of experiments where you kind of go, oh, hi, I discovered antibiotics. Now, which one is the better experiment? Do we rely on that kind of accident? I hurt my toe, by the way. I'm really bleeding now. Or do we do this kind of intensive sort of bludgeoning type experiment? These are the questions of what this definition actually entails. When was the last time you did an experiment? Beside that little refraction. It's not really an experiment. Chemistry. What kind of experiment? Tell me about it. You don't even remember? Like, I don't know, we did some stuff with chemicals, and it like bubbled.
Yeah,
What?
cross-pollinating plants.
What does that mean, cross-pollinating plants? What did you do?
Basically
Oh, that's biology.
Oh, that's biology.
We're
Okay.
just making the plant sexually reproduce in order to reproduce it. Like,
And did you actually make the plant reproduce?
Yeah, we are.
You are currently. Oh, you didn't do it instantaneously? Like, perfectly, yeah. So experiments have some time involved with them. Data? Are you collecting data? Okay. So what else are you doing? You're observing. What are you observing specifically?
The height, the color, the health, anything you want.
Oh, yeah.
Anything you want. So do you have to create your own research question involved with this cross-pollination? Okay, that's good. I like that. That's very scientific. And why do I say it like that? Because what could that kind of experiment be? When you're pointless,
Or just
Oh yeah,
you
like
know the
just
results.
here's the worksheet.
kind of like what I just did, kind of pointless, or like here, look at it. I don't know, because I'm not a scientist, but it could be exactly right. It could be an experiment that's not really an experiment, meaning here's A, here's the experiment B, and this is your intended result C. You basically learned a definition. Based on somebody else's work, you're just seeing it happen and everyone goes, yay, experiment! Right? So I like the idea that you're collecting your own data. There's a little bit more leeway there. How about you guys with chemistry? You're like, I don't
We mixed chemicals in order to figure out which chemicals produce a precipitate and which chemicals don't react.
Did you know the intended outcome before you did it?
No.
Excellent. See, we have some good science teachers for you to do. So that's
First do, but
well, of course, because it's teaching. So that goes to our ideas of it, whether or not we are doing real experiments in science. Can we do those? Well, you don't have enough background knowledge to do a real experiment. Well, you can, but we're learning. We're doing experiments as learning. But oftentimes experiments don't yield a result that's been known. So when we're doing real or theoretical science or an applied science, we're constantly trying to reassociate our hypothesis with what we're seeing about the world through these experiments. And sometimes when we are doing an experiment, we actually find a result that we weren't even anticipating, that was different in a different branch. Or maybe even like another scientist comes in and sees an experiment that's done, doesn't know anything about it, but can kind of use their own field to change the experiment and find great things as a result. This is lots of Nobel Prize winners have done it like that, where it's this weird sort of non-conventional, not what you're learning at least in school about how new knowledge is gained. So I'm glad though that you are going through a process where you're developing knowledge on your own and also new knowledge potentially, because you're choosing the data that you want to record and why. Purposes of experiments, I kind of already mentioned some of those together, to yield a result, to discover new things, to reject hypotheses, to disprove other people. So experiments are very important to that. What might be a parameter of an experiment, a valid experiment? If we were to think about not just the purpose, but the validity of it. You're taking data on cross-pollination of plants. What data are you looking at?
You can see the genotype and phenotype.
So genotype and the phenotype, that's really good. I have no idea what a phenotype is. That's,
It's just
what you
what
would
it
like molecular.
oh, right, of course, I knew that. Jeez, I knew that. I'm looking at my camera right now like, hey. Okay, great, so phenotype. What is your hypothesis? Do you have one that you're using?
Yeah,
actively?
we're doing that inbred plants will produce a less diversified outcome, and while purebred.
Do you name your inbred plants like Cletus?
This is Steve.
I'm Cletus.
Steve,
I'm an inbred. Sorry, that was white trash comment there. But okay, so what would, in order to make that experiment valid, what would you have to do in order to